logarithms in base a. So this is an obvious generalization of logarithms in base 10. So let us imagine we have a different value of base, a different number for base. So already what you know about exponential functions, if you have an exponential function f y equals a to the power of x, you know something about the value of a. The base can be positive, and moreover it should be different or not equal to 0. It cannot be not 0, sorry, but 1. It cannot be 1. So in order to have an exponential function, you have to have a positive base which is different from 1. Now here I have the green curve which represents the choice of the base a equivalent to 2. So I have the a equal to 2 in this picture. So my function f is 2 to the power of x. And here the blue one, the blue function, is its inverse. So you see it's the reflection of the original function in the diagonal of the first and third quadrant. And this function should be what we call the logarithm in base a of a number. Okay, so it's very similar to the situation that we encountered in case of logarithms in base 10. So let us look here what interesting things can we find about these two curves. So first, the green curve, the exponential curve, passes through the point 0 and 1. Then the logarithmic curve has to pass through the corresponding point 1 and 0. So you see these two coordinates, x and y coordinates, are interchanged. Moreover, the green function passes through the point 1 and 2. Well, 2 is there because we have the base of 2, we have the function 2 to the power of x, but in general case this point would be 1 and a, where a would be the value of the base, and this point is reflected to this one with coordinates 2 and 1 in our case when we have the logarithm in base 2 of x, but in general it would be a and 1. Okay, a would be the value of the base in general case. Now, moreover, you see that while the domain of the original exponential function was the set of all real numbers and its range was represented by positive real numbers, these two are again interchanged when we have to describe the inverse. The inverse has the domain represented by only the positive real numbers, and the range of the inverse is the whole set of real numbers. Okay, now let us continue with these formulae here. So the inverse function f inverse is written as y equals logarithm in base a of x. So this is an obvious generalization of the previously described case of logarithms in base 10 of x. This is how you read it. There is no abbreviation, so you cannot write just logarithm if you have a base different than 10. Only in case when base is 10, you can replace logarithm in base a of x just by logarithm of x. So then it is understood that the base is 10. But if base is not 10, you have to include it in your symbol for the logarithm. Now, the definition of the logarithm in base x, and this is the important one. You have to be able to say that in your own words and try to understand what it means. So the logarithm in base a of a positive number x. Okay, so we take logarithms only from positive numbers. The positive numbers can be taken as the input to this function. So the logarithm in base a of a positive number x is the power y that a must be raised to in order to obtain the number x. So if you want to obtain the number x as some exponent, as some exponential, so x has to be equal to a raised to the power of y, and this proper value of y that results in x as the result of this calculation is called the logarithm in base a of x. Now the obvious conditions were already mentioned, but let us repeat them again. So a has to be positive and not equal to 1. This is the obvious requirement. This is the requirement for exponential functions, and also it must be a requirement for the logarithmic functions. And moreover, x has to be only positive, because we can take logarithms only from positive numbers, and moreover, the values of exponential functions have to be only positive. You cannot have negative value or zero value of an exponential function. So these are the basic facts. Now this and this are equivalent statements, and once this is true, then also this is true, and once this is true, then the first one has to be true. So they are interchangeable. You can, whenever you have one, you can write the other, and vice versa. Now, consequences. So as I said, this statement here is equivalent to this one, so you can replace them by each other. Moreover, there is this obvious fact that the logarithm in base a of a raised to the power of y is just y, which amounts to the fact that f inverse of f of x, or actually y in our case, should be y. So if we combine the inverse and the original function in this way, what we get is the identity, okay, the identical function. And moreover, this second statement amounts to the following. It says that f of f inverse of x is just x for all possible values of x. We can, of course, get these statements also in a different way. So let me, for example, start with this one. So x equals a to the power of y, but since y is logarithm of in base a of x, we can continue and replace y by this. So it's a to the log of in the base a of x. So this way we obtain this second statement. And if I start with this one, so if I start in a way that y equals logarithm in base a of x, I can replace x here by what it is. It's a to the power of y, so I can say that it's the logarithm of in base a of a to the power of y. And what I end up with is this first statement here. So these two statements are obvious consequences of the definition of logarithm.